Hello everybody, and we are going to talk about Boxplots here. We've talked a little about Boxplots before, used them a fair bit, given you the gist of it, but we're going to get into the fine-tuned details a little here. So in their simplest form, the Boxplot is a plot of the 5-number summary. Listing of these 5 values, the 3 quartiles, Q1, the median, Q3, and the min and max. And then we have a box, so a simplest form, we have a box where the bottom of the box is Q1, or the 25th percentile. The top of the box represents Q3, or the 75th percentile. Then there's a line in the box where the median is. And it's going to be somewhere in here, but it's not generally going to be halfway, not that kind of thing. So it'll be something like that. And so that line represents the median. And then from the top of the box, we have something going to the maximum. And from the bottom of the box, we have something going to the minimum. So when there are not extreme values in the data set, then a box plot is just a plot of these 5 in this fashion. Or we could have it a horizontal box plot. That's a vertical box plot, which we will mostly use, but we do have horizontal box plots, same idea. We just have, rather than the value of the variable on the vertical axis here, we could just spin it around and have the value of the variable on the horizontal axis. I'm usually going to do these, but we'll see in a minute. I kind of like putting the horizontal one on top of a histogram sometimes. So we'll take a look. Now, that's the gist here. And the issue, the problem is, in a sense, that if we have a really extreme value, let's say we have something way out here, then this line would go all the way there, and it would just be sort of throwing us off. We wouldn't know what's happening out there. Maybe we have one single value out there, maybe they're all spread out there. It's kind of hard to say. So we think if these little whiskers, what we sometimes call whiskers, if they go too far, we think that gives us just a screwed up view. And we say, well, we don't want them to go all that far. So if they're going to go too far, we say we just stop them. We just don't let them go that far, and we plot extreme values in individually. Now, what's our rule for the extreme values? Well, there's a variety of things we could use, a variety of things we could do as far as what is extreme or not. But box plots have a bit of a special one. And the cutoff here is going to be, believe it or not, 1.5 times. The whisker length can't be more than 1.5 times what we call the interquartile range. And our interquartile range is this distance here, so between Q3 and Q1. So the IQR, interquartile range, is Q3 minus Q1, right? That's our interquartile range. And we're going to say, just sort of casually here, we'll illustrate it in a second, that we're not going to let these whiskers go out, have a length of more than 1.5 times that distance. Intuitive, right? Okay, so it's not that intuitive, but there is stuff that goes into this. We're not just pulling this out of nowhere, okay? There's some thought to this, and we can think of it as a rough rule that works pretty well. And sometimes people have different things, different guidelines, all of this kind of stuff. This is what I'm using, all right? So this notion, and this is quite common as well. I think this is what we need. It's a bit of a problematic enough to figure out exactly what's going on. So, for now, we're going to look at it in complete detail here. So our box plots, the ones we plot, the ones I've looked at so far, are like this. So we still have this box extending from Q1 to Q3. We still have the line through the box at the median. We're still doing that. But we're having this upper whisker that extends from the top of the box to the largest observation no greater than 1.5 times the interquartile range above Q3. And anything above there, we're going to say is an outlier, and we're going to plot it in there individually. Or let's say it's an extreme value. It's getting plotted in there individually. Same thing on the bottom end. That lower whisker is going to go from Q1 downwards until it hits the minimum, say, but not if it's farther than Q1 minus 1.5 times the interquartile range. So the whisker, either the top this top whisker here above Q3, this bottom whisker here below Q1, we're not letting the length of that be greater than 1.5 times the interquartile range. So when we go up here, we're stopping here. The largest observation that is not greater than Q3 plus 1.5 times the interquartile range. Anything above there gets plotted in individually, in dots, asterisks, stars, lines, something. Depends on your plotting software or what you choose to do. Here, right, the same thing. In this situation, it did go to the minimum because in this fabricated example that I have, this distance here was not greater than 1.5 times the interquartile range. So this stopped at the smallest value in the data set, and there were no observations less than Q1 minus 1.5 times the IQR. No outliers on the low end. So that's what the box plots are doing. They say this is going to get too distorted. The view is going to get too distorted if we just let that whisker go on forever. So we really should plot extreme values in individually. And that's what box plots do. They do illustrate the shape of the distribution, but the killer app of box plots is comparing groups, as we've talked about many times. So let's look at a situation where we might do that. So here's an example from my university and likely yours, the University of Guelph. Study investigated jumping characteristics of the mangrove rivulus. And before being subjected to this jumping bout, we had some of these fish kept in water, some out of water, and some were out of water and then put back in water briefly. These are fish that are really cool and can jump, and part of the things, right, they can jump out of the water, go across some land, and hopefully find a little bit better water for themselves. This is sort of the idea. So a jumping bout, they get prodded with a little pin or something. So if we take a look at this, we're prodding until they jump like this, and they're hoping to get to a safe place for them, I suppose. And this particular scenario, they're going to be prodded until they stop jumping, the poor little fellas. But one of the measurements was the number of jumps before they stopped jumping. That was one of the measurements. So we have these three treatment groups in this in the experiment. We've got the control group that were kept in the water. We've got the ones that were kept out of water, that air group, and then the ones that went back in the water for a short bit, the recovery group. So we've got these three groups, and we're comparing them. And so the killer app of box plots, we have discussed this a fair bit, is in the comparison of groups. And if we were to look at this, this vertical axis has our number of jumps, so the value of the variable there. The width of the box plot here means nothing to us. Okay, it's just visuals. I could have made that really skinny. There's an option in R. You make the width really small if you wanted to. That width doesn't mean anything here. Sometimes people get fancy box plots and make it mean something. I'm not going to. The width is just a visual thing. If it looks too skinny, it's too skinny, right? Too fat, it looks silly. So I have it looking something like this. So what would we say then? If we were to look at this overall, it looks like perhaps this air group has a tendency to be a little higher, right? Overall, that's one of the visual takeaways we might look at. Maybe there's not a big difference here between the control group and the recovery group. Nothing too visually different there. But maybe with this air group, like just a hint, we haven't crunched numbers, we haven't done any statistical inference, that sort of thing. But visually, we'd look at that and say, hey, maybe that air group is a little bit higher there. Maybe when they are out of the water for a little while, they're at the ready to jump, and they have it all ready to go, and they've got a little bit more endurance in the jumping, in jumping. And who knows? We'd have to crunch some numbers. So we would analyze this later on. We could go and do something perhaps like a one-way analysis of variance, something we'll learn later in the course, to investigate these differences and try and see if there's a statistically significant significant difference in there somewhere. So we might investigate that, analyze that, crunch some numbers, do some statistical inference. But for now, it's suggestive that that error group might be a little bit higher. Now, box plots do tell us something about the shape of the distribution, and they're reasonable for that. But often histograms are a little bit better for that, especially if we have a fair number of observations. So if we just thought of the shape for a minute here, looks like the control group here, that looks roughly symmetric to me. Same as the recovery. I mean, this tail's a little bit longer than that tail. The line's a little bit higher, but overall I'd say that looks roughly symmetric. These two look roughly symmetric. It's in the error group that perhaps we see it, suggestive at least, of that being stretched upward a little bit. And that's indicative perhaps of a little right skewness, like it's stretched upwards. The large values are a little larger than we'd expect them to be. If it was, for symmetric distribution, so there's stretched out that way a little bit. So it's suggestive of that. We don't have any outliers in this particular plot. No outliers in this particular plot. But this overall, we've done this for a while. The killer app of Boxplots is in comparing groups. But let's say we wanted to get a little bit more feel for the what Boxplots tell us about the shape of the distribution. I think an underused plot is this notion, where we put a horizontal box plot on top, above a histogram of the same data. So this is helpful in a couple of ways. One, for illustrating a distribution, but two, for giving us an idea of what a box plot is. So if I go over here and look at this one, roughly symmetric distribution, we see this horizontal box plot looks pretty symmetric. Has one outlier out here, one extreme value out here, according to the 1.5 times the interquartile range rule. But overall, that looks pretty symmetric. If we go over here for this right skewed data, well, we see this type of thing that we tend to see, these box plots for right skewed data. We have, what do we have here? In the box, this median is a little closer to Q1 than to Q3. So the median isn't halfway in the box like this one was in the symmetric sort of situation. It's a little closer to Q1 than Q3. The box is stretched here. This upper whisker is longer than this lower whisker. So that's stretched there. And we've got a few outliers here, these extreme values that we're seeing down there. So this box plot, it's like a symmetric one, except stretched this way. And we can see in the histogram that that's a right skewed distribution. And this is what we'd see if we had a horizontal box plot stretched out that way. If we did a vertical box plot, then it'd be stretched upwards, right? It'd be stretched upwards. That's the value of the variable on the vertical axis. It'd be stretched upwards there, indicating right skewness. So these plots are sort of a nice little type of plot. I like these ones where we can figure out where Q1 is on the histogram and Q3 and these outliers, and we can get some of those summary statistics and map them to the histogram rather easily. People don't do these plots a lot, but I actually quite like them. Simple idea, but quite nice. And one last thing about box plots, at least for now, is that there does tend to be a bit of a sample size effect, especially as it relates to the outliers. So like I say here, using the box plots to compare variability between groups can be a bit misleading, a bit misleading if there's a big difference in sample size. So as the most extreme values in a sample, well, they'll tend to get bigger as your sample size increases. Those extremes that push out a little bit, as well, we'll tend to see more outliers, at least in a box plot sense, when we get a larger sample size. So to illustrate that, I'm going to sample values from this standard normal distribution. Nice bell-shaped curve. This is going to come up for us a lot later on. this normal distribution, going to come up a lot. But for now, we're going to randomly sample values from this distribution and see what happens. So if I draw a random sample of size 20 from here, plot it out, looks like that. If I were to draw a different random sample of size 20, it would look a little different, but just overall get the big picture vibe here. If I draw a random sample of 100 observations, look like that. Now 500, 2,500, and 12,500. And one of the things that's most evident here is when we have 12,500, we have a lot of outliers. You got a lot of outliers here, a ton of outliers, lots of outliers. At 2,500, you got a lot of outliers too, right? A lot of outliers. And as our sample size increases, we tend to see more and more outliers by the boxplot outlier rule, certainly. And overall, just sort of a little bit of a little casual notion that might help for larger sample sizes, we tend to see by this boxplot rule about 1% of them being outliers and drawn in individually. So what happens when we get really large sample sizes, we get these more outliers here like this. And so then, like overall, if we looked at these box plots in terms of, let's say, what's happening between Q1 and Q3 with the box, there's not a lot going on here, right? They're a little different all the way along, but overall, the vibe of the box plot is very similar when our sample size increases, except we're really getting more and more outliers here. And so if we're comparing something with a very large sample sizes to something that's a little smaller, like let's say comparing this to this, even though overall the situation is very, very similar, we're going to look at this one and think, oh boy, there's a lot of outliers there. Maybe there's more extra variability or something weird going on. When in reality, nothing weird's going on. Both are samples from this standard normal distribution. It's just that this one had a lot more observations in it. A lot more chances for outliers to happen. So when we've got box plots of sort of vastly different sample sizes, especially, that can be a bit of a distortion there in terms of variability, a visual distortion in terms of variability. We have to be a little bit cautious. This is really only an issue in the extremes. If with one sample size of 100 and others 150. No big deal, but just something to be aware of. That's it for now.